And this is the second episode of building a computer in Fallout 4, the series where you'll learn how computers work by building one in the game Fallout 4. Now, last time we showed you how to make logic gates using just switches. And there was actually a comment on the last video. Someone said, if you're making a computer in Fallout, you could make the game Fallout in Fallout. Now, that might have been a joke, and I certainly won't do anything like that, making Fallout the game in Fallout. But there is an idea in computer science known as something being Turing complete, named after the Alan Turing. What something being Turing complete means, it can calculate or do any kind of mechanical process that any other computer can do. And so what that means is, I really need to send Nick Valentine somewhere else. I just have him as my companion for some of the things I was doing. What Turing complete means is that if this computer were Turing complete, it could conceivably do any kind of calculation that the the PlayStation 4 could do. So conceivably you could have the game Fallout 4 in Fallout 4. But that's completely impractical for a few reasons. One is the speed. This will be far slower. Basically, a game running on the PlayStation 4, it would probably take more time than you will be alive to run on this computer. Another reason is the size that we'll have to build with. As you saw, the logic gates that you can make in Fallout 4 were about, like a foot width in game measurement. So this computer will be huge. And in fact, I'm on Abernathy Farm because I heard that this is one of the biggest places that one of the biggest settlements you can build in, both in terms of area and height. That's one thing I found, is that some places you're limited to height. At least in Hangman's Alley, you can't build above the buildings. So that's about 3 floors. But I hear that you can go pretty tall in this one. They probably made it so that you can build up and around the tower here. And also, I think Finch Farm, it's called. You can build all the way up to the freeway overpass that's over there. I know you can build up to there. So that's another reason, is that there's no way we can fit a gig of this kind of memory. We may have, tens of memory addresses instead of billions, if I can find that much copper in the wasteland. And speaking of large computers, if this Fallout computer interests you, and you like other big, impractical computers, then check out something called the Mega Processor. Just do an internet search of Mega Processor, one word. I think you'll find megaprocessor.com. Someone made a processor, or a computer kind of like this, from the ground up, but using individual transistors, and those are, like a quarter of a centimeter thick, so far smaller than pieces we'll be using in here, but it still ends up being pretty huge. It's just a few, I don't know, is it 8 bytes, or 8-bit computer? Maybe, but it's not huge, and it is, I think they said 10 meters wide and a couple meters tall. So That thing will takes the space of an entire room, and that's just a very tiny, kind of simple computer. Same thing with what we'll be building here, except it'll probably take up not just a room, but like an entire settlement. And yeah, speaking of with the yeah, and I think the site for that is megaprocessor.com. Just do a Bing search for it, Lycos, whatever you want. I think it's megaprocessor.com. Speaking of the individual parts that uses, so in the last episode I mentioned that this uses switches for its basic component, and was talking about relays that when one signal comes in, it activates an electromagnetic relay. Actually just saw, it seems like there may be a viewer online. Wow, I think that's the first time while doing live. In the last video I mentioned the switches worked with relays, which used electromagnets to close a switch. Now, in your typical computer that you have in your phone or your PlayStation 4, the switches are microscopic, but they don't use relays. They don't use tiny electromagnets to close switches. Instead, they use transistors, and those pretty much act the same way. You have a signal coming in, and it closes a connection just like a relay. But we don't have those in our Fallout 4 world. We have just giant switches and foot-long logic gates. And in the last episode, we use those switches to make logic gates. Showed you how those work. And I said in this episode, we will be showing you how to go from logic gates to performing math and how to represent numbers using just logic gates. So when you think about how we represent if we want to think about how to represent numbers in a computer, let's first just think about how we normally represent numbers. When you write down numbers, you write them in a row, and the rightmost is the least significant digit. This is just, its value is 8 right here. And then you go over, and here's the tens place. So 0, we have no tens. And then one more over, 100, so we got 100, and so on. And what you do is you add all of those places together to get 108, say, for this. All right, we all know that. Now, what happens when we increment or add 1? Keep in mind, we only have 10 digits to work with, 0 through 9. So what happens when we use up in just one space? Let's count up. So there's 9. All right. And then what happens? This rolls back to 0, and then increments the next one, and so forth. So that's how we do it in our regular base 10, where we have 10 digits, 0 through 9. But in computers, we, as we saw in the last episode, we just have 2 values, 0 and 1, just signal or no signal on the wire. Now, let's change our counter to do that, to be binary, having only 2 digits, 0 and 1. So we'll just set the count to 1. Leave my gun out. What am I doing? So when we increment in binary base 2 numbers, so in binary base 2, this is, again, the ones like before, but only goes 0, 1, and then cycles back to 0. This, when it was base 10, this was 10 to the first power. This was 10 to the 0, or 1s. This is 10 to the first power, so this is 10s. Now in binary, this is 2 to the first power. So these are the 2's place right here. Either have 0 or 2. And then like when we were in our base 10 number system, this was the 100s, or 1 to the second power. So you can see 0 power, 1 power, 2 power. So in 10s, this was 1s, 10s, 100s. And like in binary, this will be 2 to the 2 power. So this is a 4's place. For each value here, you multiply it by 4. So you can either have 0 or 4. So when we have this number, let's see what it is. 0, so no 1s. 1, 2, so that's 2. And then 1, 4. So altogether, this is 6. Like if this was base 10, we'd count 10 and 100, so 110. But this is in binary, so this is 2 plus 4. So that's 6 in binary. 1, 1, 0. Now let's increment again. Went up by 1, so then it's 6. It was 6, and now it went up by 1, so that's 7. Now what happens when we roll over? Well, we go back to 0. That's not a good example. So let's say we're at 1. Oops, I did that twice. So 1. What happens when we want to go to 2? Now there's no digit number 2 in binary. So that means that rolls over, and the next place gets 1. So we went from 1 to 2. So that's a 1 in the 2's place, plus 0. That's 2. So that's really quick how to represent and count up by 1 in binary using just the digits 0 and 1 that stand, and the places stand for powers of 2. So let's look at this handy chart about what happens when we add. So let's say we have 2 inputs when we add binary numbers, A and B. They can either be 0 and 0, and the result is 0. You can either be adding 0 and 1, and the answer is 1. Or you can add 1 and 0, the answer is still 1. And then adding 1 and 1 is 2. 1 and then 0. Hi, Nick. Now, when you add, you have a sum. That's when you have just the same place you were adding in. And then if you get too big and roll over, you have a carry. That's kind of like when you add your normal base 10 numbers. 6 and 8 is 14. You put the 4 down there, but you're not done, so you have to carry that up there. And then you add all 3 of those. 1, 5, 7 for 13, 134. Do the same thing in binary. So let's say we have 3, that's 1, 1, that's 2 and 1. 3 plus 1, we know that's 4, so going kind of how we did for the 10s. 1 and 1 is 0, carry the 1. 1 and 1 and 0. That's 2, 1, 0, so kind of just imagine you carried that 1 up there and then it just dropped right down. So that's why we need a sum place and carry. So when we add 2 bits together, that's called just one digit in binary, a bit. When you add 2 bits together, you need 2 signals coming out, the sum and the carry. So how do we do this in logic gates? Well, if you look at each of these, the sum and the carry, think about what we talked about in the last video in some of the logic gates. If you'll remember, the sum looks like exclusive OR. That's when the output is 1 when only one of the inputs is 1. Or it's 0 if all of the inputs are the same. So 0, 0, that's the same, so output 0. 0, 1, they're different, so output 1, Same thing here, they're different, so I'll put 1. 1 and 1, they're the same, so I'll put 0. The carry looks like the AND operation in logic. So when you carry, you only get that 1 if both inputs were 1. And so that's AND. So let's make our... I'm going to send this home.
I'm listening.
Hey, Valentine.
Something to get off your chest?
Yeah, you're...
Probably about time we parted ways.
Sure.
Go to Sanctuary Hills. You're messing up my little video. Okay, so we're going to have the exclusive OR and the AND operator. Let's pull this up. Go into our power. We'll get the logic gates out. So here is our AND for carry. Let's see, I'll put that there. And exclusive OR for the sum. Working with this, I found that the logic gates snap on the top and bottom, but not on the sides. That's somewhat helpful, but interesting choice. So let's get some inputs. We'll use switches. Let's see, power pylon, no. Switch pylon, yes. So this will be our input A and our input B. So let's connect power. Now A has to go to each of these, because each of these gates have input from both. And let's add some lights so that we can see our output. I find these conduits are new to the contraptions workshop. I find that they work pretty good. Add one conduit there. Another conduit there. Add a light. Add a light. Make sure they're not connected. That would be a mistake. And then, let's see. So the AND operation was our carry. So we'll take the output from here. And this light will represent our carries. And exclusive OR is our sum. So this light will represent our sum. Now let's turn these off. Start from 0 and see if we have this right. So bits 1 and 1 added together should be 0. And lights off represent 0. Now let's add just 1.
Hi guys.
Oh, and my wife came home.
All the guys. Hi guys.
Say hi. I'm streaming a Fallout video.
Oh, sorry.
So we're adding 1 and 0. Our carry out is 0. There's nothing carrying out. And our sum is 1. So that's right. Let's try it the other way. See how that works. Okay, we have carry is still 0. And sum is still 1. So that works. Now let's add 1 and 1. Our carry is 1. And our sum is 0. And if you remember, like in our binary numbers over there, if this is the 2's place and this is the 1's, then that makes sense. So this is 0, or this is 2. 2's place is on, 1's place is 0. So we're showing 2 here. So there we go. We added our first number just using switches and logic gates. And a lot of copper that I had to scavenge in the wasteland. Now, a usable computer should be able to add more than just 1 bit. So when we wanted to, we saw here we had one number. When this incremented to 2, it rolled over into this one, and when this rolled over, it incremented in that one. What that means is that when we add in a lower place, we have that carry signal. It has to go over to another place and get added there. So what we need is, let's pretend that we are building a circuit for a middle bit. It's in the middle, so that means it'll have input for 2 numbers, A and B, but then there's got to be the previous place's carry going in. So we need 3 inputs. We need A, we need B, and we need a carry signal to come in. Now, so that means adding 3 bits together instead of just these 2. So how do we do that? Well, we can just add the 2 bits and then have another adder adding the carry and this sum bit. So let's do the same exact thing here. Let's get a carry and a sum bit gate. So we'll have, here's our AND gate. We'll just put that about right there. Then we'll get that exclusive OR. Snap that there. And then let's pretend that there's a carry signal coming in. So this is the carry. Power that up. Yes, power. Have this go into the input for here. Now, which one? That's right. So the sum for this one will then get added. So here's the sum of A and B. We then want to take the sum of this and then add the sum to the carry in. So we go from here. Okay, that worked. Here to here. Okay. And the carry also goes to both. Why does it not want to go there? That's interesting. We'll try going from the gate to this. Wow, it does not want to do this. Okay, we'll try moving you. Oh, it's already connected. Ah, it wasn't showing the wire. Yeah, things get weird when you have this many wires. I think the rendering gets confused. So, like, do you know we gotta go with this one for the carry. There we go. So, we still have this carry, but this is no longer the sum. Let's get rid of that wire, because what we have now is this one is now the actual sum. So this one will go here instead. And this one's not the carry. Okay, so what if we have a carry from here? We can either get a carry from here, or we can get a carry from here. When we have a carry in, let's see. Yeah, if we have a carry in, or a carry from the A and B, that means that the sum going in here will be 0. But this carry could be could be 0 or 1. So we either get a carry from here or we get a carry from here. And since that's, I said or, that means we should be using an OR gate. We will have a carry if either one of those is true. So we'll have it, I'll just put it there. So we have a carry from here, or we have a carry from the carry in. And now this is our actual carry. So let's reset everything. Let's just make sure that still all works. We'll go through our normal having A and B. 1. Oh, something did not work. Let's see, sum goes here and there. Oh, that's right. Let's see, this maybe is this. Nope, not there. I feel like one of these wires disappeared again. I can't see it. Yep, there it is. That is annoying. Well, that's neat. So let's see, we do have this going to both. So basically, this one should be lighting up. I'm gonna get rid of that. I'm gonna say go from here to here. See if that connects. There we go. Oh, I see how this works. So you have to say, you have to go from here to here. These logic gates can be finicky when you're building with them. Okay, so we have 1 going in, and 1 is our answer. Let's switch the inputs. 1 plus 1, and we get 1 out. Great. Let's add both. 1 plus, or that was 0 and 1, and then we had 1. Now we have 1 plus 1, and 2 is our output. Great. Let's see how that all works when we have a carry in. Does not work at all. That's fantastic. So carry in should be going to both of these inputs. It wasn't going to both inputs. Okay, and I couldn't tell because sometimes the wires don't render. This is going to be fun building this computer if I can't see the wires. So we have carry in. So 1 plus 0 plus 0 is 1, as we would hope. Carry in plus 1 is 2. Great. Let's try the other input. Carry in plus 1 again is 2 again, as we hope to see. And now carry in 1 plus 1 plus 1 is 2 and 1, 3. There we go. Now, the difference between when we had just that one, adding just 1 and 1 bit together, not worrying about carries, that's called a half adder. And now that we are dealing with a carry in, that is called a full adder, because as you can see, you had to use 2 half adders to get a full adder. It's like they thought through those names. It's like they thought those names through. So with this, we can then make our adder. So we will, let's see. We'll split up these inputs. Do that. This will be B. We'll put the B's over here. And we don't need that. I'll just disconnect these. So disconnect that, disconnect that. This will be our lower bit for our B. And we need another higher bit for B. Or rather, another lower bit. So this will be the lower bit. Oh, that's right. That's not right because I disconnected some wires. So that's going to be funky for a little bit. So, we want to have another bit for our binary number. So what we're going to do is, like we had here, where you had ones place and then the twos place, we're going to have two 2-bit numbers, and we're going to add those. We're going to go from adding 1-bit numbers to 2-bit numbers. And like before, this one will represent the ones place and the twos place of A. So we'll call this A0, A1. And likewise, this will be the lower bit of B, and this will be the higher bit. So this is the ones place and twos place of B. This will be B0, B1. Now, like we said, the higher bits need a carry in. So we already built this with these here. It's got a full adder. For these, when you're in the ones place, you don't have a carry in coming into it. There's nothing before it that you're adding in. So we can just, as before, we can just use our a half adder. Now, so let's build a half adder for the A0 and B0 bits. So let's see. We will have this here for a carry out. Then we had exclusive OR for our sum. And let's see. This needs power. And that already had power. I'm glad that wire is visible. Now we string up A0 to the first half adder, and then B0 to the first half adder. There it is. Let's see, that's on. That's already on. I'm just gonna take a moment and turn everything off. So when we get this done, we're looking at 0 plus 0. Just a good place to start. So we said that this was like the ones place. So that means the carry out should go to the carry in half adder of our full adder. Uh-oh, I got a feeling like it's not displaying. There we go. Hi. So there's the carry out. And now the sum, we need to make another light for that. So this will be the ones place. And the sum will go from there. Okay. There we go. I think that should be our 2-bit adder. Let's see. So, remember, this is A, and this is B. They're 2 bits. So let's cycle through. So, right now, we're adding 0 and 0. Nothing's lit up. That sounds about right. So let's add 1 and 0. 1. That sounds right to me. Let's add 1 plus 1. 2. Looks great. Remember, 1's place, 2's place, 4's place. So we have 1, 2, and nothing else, so the answer is 2. All right, let's add... let's just cycle through some numbers. So let's add 2 and 0. Remember, this is A. This is A's 2 place and the 1 place. So to make A equal 2, turn on the 2 switch. And that's kind of close. That's not on. Oh, wait. It's not on. Interesting. That should not be on. Whoa, there are some very incorrect... Wait, no, that's right. So let's think through this. This is the sum. The sum goes into the carry and carry. None of that's on. And that only goes to the sum. Right? Oh, I got something messed up here then. Alright, we are adding 2 and 0. So, in the 1's place, that's all off as it should be. We can forget about that. So what should be happening here is adding this, since this is the 2's full adder, we should be adding basically 1 and 0. Oh, you know what? I don't see a wire coming from there to there. Nope, it says it has it. Okay. Yep, there it is. Oh, this is gonna be fun. Not seeing wires. So that has A1 and B1 coming in. Correct. Sorry, this is something that you may be seeing a lot of, is just debugging. I did run through this before doing this, and everything was working fine. Okay, so we have all that. So, this one should not be, no, that should be on, because we're adding 1. And there's no carry out, because it's just 1. So that's fine. So we do have a sum here. That should be good. The AND should not have this. So I don't believe that this is connected to one of these. Which one is it supposed to go to? Oh man. I really don't like not seeing these wires. Yep. Okay. Seems like I didn't get the carry out from here to go to here. Yep. That got it. Okay. Sorry about that. So we're adding 2 and 0, and we get 2. Great. Let's add 3 and 0. 2 and 1 is 3. Awesome. We did 1 and 1. Let's do 2 and 1. 2 and 1 is 3. 3 and 1 is 4. Now remember, this was the 1's place, 2's place. The next power up for 2 is the 4's place. So that's 3 and 1. Let's see, 2 and 2. 2 and 2 is still 4. Great. 2 and 3. 2 and 3 is 1 plus 4. 5. Fantastic. Let's see, 3 plus 3. No 1s. 2 and 4. 3 and 3 is 6. Or 2 and 4. So there we go. We built a 2-bit adder, going from switches to logic gates. We made an OR gate. We made a full adder that can add a bit plus a carry in, and then we use that, added another half adder to make a 2-bit adder. And then we cycled through, enough of the, maybe all of the inputs, I don't remember. But enough to see that our adder works. And so there you have it. Thanks for watching. Not sure where we'll go to the next episode. Maybe a little bit, show you a little bit more about arithmetic in computers. But that's it. Go ahead and leave comments on the video. This is live streaming right now, but then it will be archived on YouTube. You can also comment on our various social medias and everything. And while you're here, why don't you go ahead and subscribe to Permanently Geek. That way you can get updates on this series. And check out all of the other videos on this channel. Permanently Geek does a lot of really good stuff. Music, movies, video games, a lot. So thanks again, and we'll see you next time. I gotta figure out how you stop streaming. Let's see.